So thank you everybody for coming to this. As you may notice from all the technical difficulties, this is the very first time we've ever tried to do this, and there's a very small group of people running it. So thank you all for bearing with us. So I'm Ben. I'm a graduate student in the Meiler Lab. Today we're going to be starting our workshop on drug design using the biochemical library software that the Meiler Lab has been developing for the last 2 decades now, and also going over how we've integrated this functionality into Rosetta to do some super cool stuff. So to kick off the event, we are going to have the man himself, Dr. Jens Meiler, give us a history of the BCL to sort of let us know how it started, what his sort of goal with it was, and how we sort of got to where we are today. So without delaying any further, I'm going to go ahead and let Jens chat.
Yeah, so thanks Ben for the kind invitation. It's a great pleasure to kick off this workshop and tell you a little bit about where this topic comes from. And so I didn't prepare sort of a traditional presentation. I have a few slides that I'm going to share and a few anecdotes, I guess. But let me go ahead and start with how I got into this whole business and what the BCL is and entails. And so this goes back a few years. Host disabled participants screen sharing. I think that could become a problem. Let's see if some host can fix that. And
we're on it.
Okay. I was still host is disabled. So I'm waiting. So I was a diploma student. Today you would say a master student. I studied chemistry at Leipzig University. Actually, even as an undergraduate student, I studied chemistry, but I was really fascinated also by computer science. I couldn't study computer science because my mom was a professor of computer science at Leipzig, right? And my dad was a professor of physics. And so I couldn't study math or computer science or physics because I would have had a ton of lectures with my parents and they would always have said, here's the sun off. So my way out was to study chemistry, which I really loved, but I still took a bunch of computer science classes at the time. And this was in the 90s, 1989 to 1993. And so at the point, people started to play around with something called artificial neural networks, artificial intelligence. And I was really fascinated by that topic. And so I got into a group of scientists mostly in Germany, I guess, who explored these topics, something that still exists from the German society, chemistry society, the GDCH. They have a special group, CIC, Computer Information and Chemistry, or something like that, SIC. So you can join if you happen to be a member of the GDCH, you can join the SIC subgroup there, and they have conferences and stuff. I think I'm actually presenting at their next meeting. And this group was founded by a guy, Johann Gasteiger, who was a professor in Erlangen at the time. And he had a friend, Jure Supan. I think that it was some Scandinavian country. I'm very sorry, Hungary or Czech Republic or something like that. I would have to look it up. I'm sorry. But the two of them really pioneered a lot of the early work. Erlangen has actually still today a computer chemistry center with multiple professorships. And I think Gasteiger is still around. I tried to invite him to Vanderbilt at one point to give a lecture, never never materialized. I think he said he would come, but then we never sort of found a date and stuff, and I didn't follow up. But I was just starting my studies as a student in Leipzig, and they had these annual workshops, and I just my mentor in Leipzig was Reinhard Meusinger. He was an NMR spectroscopy person for small molecules, and he took me to these conferences and listened to the presentation, and ultimately, present posters myself. And I found that really really stimulating at the time. And so one of the so I started to play around with these neural networks. One of the first papers that we published was in 1995, which is sort of, it takes the NMR spectrum of an alkane, and it predicts the boiling point of that molecule via a neural network. So what it did is it took the 13C carbon NMR spectrum, it split that up in just 5 regions, 1, 2, 3, 4, 5, and just counted how many carbons have signals in that region. And if you know carbon chemical shifts, whether this is an elongated or a branched alkane, it shifts the carbon chemical shifts quite substantially. And so the number of signals in each of these regions indicated more or less how branched this is, which is a good predictor of boiling point. And so we trained a neural network to predict that. And I think I took that to Jugendforscht, and I got some prizes there with this thing. And we also published that in this series, which really came out of this workshop. But at the time, there was no software library to train neural networks, right? So I think the work that is published in this paper, I don't remember, but at least my early work, probably the one published in this paper, was really done with a software that I purchased for 40 marks from a guy in Israel who had programmed a neural network software, and I forgot how it was named, something like WinNN or something like that. I think it was WinNN, Windows Neural Network or something like that. And so he had programmed the software, and that was very exciting. And then, see, I wanted to find that, and I didn't really do it. I'm not sure I can do it on the fly right now. There was one paper that really impressed me, right? When you read your first papers, you read every word, and this one paper had really explained in great, I think they were also predicting some property of alkanes with a neural network, but that paper really was awesome in the sense that, yeah, so this is where I got the idea from. Oh my God, I don't even have the, maybe I find it if I type it into Google these days. Let me try. So I found the paper, and they really, I know that's my own work. That's not what I was looking for. So I don't even find the paper online right now that they published. 2 guys from France, and they did the same thing. They determined boiling points of alkanes with a neural network. Just I didn't like the method. They didn't use the spectrum. They used the chemical structure, and it wasn't by far as good as the thing that I did later on. But they had a step-by-step. Here, give them credit. Driss, Scherber-Croy, and Didier Willemine, and they really France, here you go, and they, I believe, had in there, you see, a detailed step-by-step pseudocode how the backpropagation algorithm works. And you won't believe it, but this is precisely what I programmed into my C++ code, or C code at the time, I should say. So I didn't like how they encoded the alkanes, so I hated that part of the paper. But from here, I really learned how to write the code for the neural network. This section of the paper is what I translated into code. And here you know why I tell everybody the neural network does not have input neurons, because the way they showed this, it looked like there were input neurons. So the neural network I programmed first time had neurons in the input layer, and it wouldn't get the same results as the win and n code that I was benchmarking against, until I understood that there are actually no input neurons, but just inputs. And so, yeah, so basically, that was the starting point of what we call the BCL today. I created this class. This is not the current version of the BCL. That's also not the first version I wrote, but it's some intermediate version from some year that I dug up, that sort of defines a class of a neural net. And then there is a bunch of code that in a very efficient way, for the time, allocated the memory and used pointers to, and very, you know, it was optimized for speed. It was, I believe, at the time, one of the fastest implementations of a neural network. And you could read it from a file, write it into a file, and you could, you know, actually you could export the code. It would write you C++ code that you could integrate into another program. So write code and file would create a very fast code that executes your neural network. I think the BCL had such a function, and it's probably still has. And so this is what later, you know, became the BCL. And you see this star nor plus plus. So it's a pointer, and we do some operation, and at the same time we jump to the next point in memory. So it, you know, all manual speed optimization that I did with some guys at the computer science department in Leipzig to make it fast, because at that time computers were really slow. So why was I excited about that? Well, I was excited about that because of structure-activity relations. You know, predicting the properties of molecules from the NMR spectrum is nice. Actually has some application. If you think about taking a spectrum of, say, blood or urine from a patient, and you want to predict, you know, whether that person is sick or not, you could do this, and people do this with these type of technologies. But I was really excited about drug discovery. And so we wanted to really take the chemical structure of a small molecule, translate that in a bunch of numbers, it could be thousands, and then train a neural network to predict biological activity. And that was really what I got so fascinated about. And so I needed, in addition to the neural network, which I just showed you, I needed functionality that would take a chemical structure, compute the three-dimensional structure from that, compute some properties, some descriptors of that structure that can be fed into a neural network, and then predict the biological activity. In these studies, usually there's a lot of cross-validation and testing and other things done. And all of these things I sort of tried to capture in the biochemical library at the time when I was still an undergraduate student. And it sort of continued while I was a graduate student. And then when I became a postdoc, I took these technologies to the Meiler Lab. And some of you know that I was one of the first chemists in the Meiler Lab, and I happened to, oops, no, I stopped screen sharing. That's not what I wanted. I happened to program Rosetta Ligand sitting next to Aura, actually, who was working on peptides at the time already. And a lot of the processing of the data for Rosetta Ligand I did with this library. It wasn't called BCL at the time. It was a directory in my computer called own, my own code. And but a lot of it was not ported into Rosetta, mostly because Rosetta was at the time Fortran, and all of this was already in C, and also because sorry, am I sharing the right screen? Just want to make sure that I'm not showing you garbage, and also because you know, there was just not time. This was already several hundreds of thousands of lines of code, and I didn't have time to put this all into Rosetta and by no means translate it into Fortran. That was a no-go. And but I can show you. At the time, I was I wasted a lot of my time still. So let me see if I can get this started here. So here is actually the neural network program. So I wrote a Microsoft user interface, graphical user interface for training a neural network, and you could load your data. I'm not sure I have an example here. Let's so there are a bunch of examples here. I'm not sure I have anything that that is nice to look at. Let's say secondary structure. So that's secondary structure prediction, and then you could, you know, load your data and do the training. I didn't, for some reason, I didn't copy my simple example file here. So let's not worry too much about that. But it could. Oh, I think I have it actually. Let me see. File exit. Let's restart this, and I can show you. The code, there was an ANSI C++ code that would compile on Linux and Unix and whatever you liked and Windows. And then there was this graphical user interface, which was done with Microsoft Foundation classes. So let me, yeah, here is XOR DAT. Some of you will know that the simplest neural network problem, simplest problem that you can't really solve with a multiple linear regression is this XOR problem, where you have two inputs. If the inputs are the same, the output is yes. If the inputs are different, the output is no. And so that's this, right? Two inputs, 0, 0 gives a 1, 0, 1 gives a 0, and so on and so forth. And now I loaded that data set, and technically this program, I think if we set max iteration to 0, and then it's freaking fast, so we probably don't want to see too much. We can just start the training, and this one gets stuck somewhere, but then you can dice, you can hold the dice, and then you get, let's stop this thing. So, okay, now you have a prediction here, a training result, where you have the desired result 1 and the actual output is 1. And so it really found a set of weights that achieves that quite easily. It's a very small network. Input sensitivity, it would show you that both inputs have the same importance. What a surprise, but that's obviously, here's the structure color coded by the strength of the weights that connect those, and so on and so forth. So you see, I put some time into that at the time, but luckily I programmed it so that all the actual work was done in Unix and ANSI C++. And so just to reiterate why are neural networks so good for drug discovery. This is again, many of you will know that, but just to explain what does this hidden layer do, right? What is this hidden layer? In this case, we have 5 inputs, and we have 1, 2, 3, 4, 5, 6, 10 hidden neurons. So all spectra, all input is translated into a 10-dimensional space. This is a lot. You could probably solve this problem with 2 or 3 neurons, but it happened to be 10 at a time. So let's say your spectrum is translated into just 2 numbers here, which is the output of these 2 neurons. And so you are projecting from a 5-dimensional input space in some hyperspace of other dimensions. And so if you think about this, let's say we have a set of inactive molecules, a set of active molecules, red and green. We would not expect that all the actives have the same molecular weight and all the inactives have a different molecular weight, right? We might have, if this is molecular weight, we might have some islands, some smaller molecules active, some molecules with a higher molecular weight active. And then on the other axis might be number of hydrogen bond donors, and there's no reason to believe that needs to be precisely one. There could be multiple solutions. And in reality, you don't have 2 dimensions, you would have 1,000 dimensions describing the structure and the properties of that small molecule. Just choose 2 here because we can think of this, right? And now we translate in this space, in the space of these descriptors, there's no linear operation that separates active from inactive. And that's what the hidden layer is for, right? The hidden layer is supposed to project these molecules into a different space, into a hyperspace. And in this case, it's a very simple hyperspace, right? It's just 3 dimensions. But in that hyperspace, there exists a linear operation separating active from inactive. And that's, in a very simplified way, what these shallow neural networks are doing. These days, everybody's doing deep and fancy and whatnot. At this time, this was all shallow. You project a set of input descriptors into a space where you can separate active from inactive with a linear operation. Or you could predict activity with a linear correlation or something like that, right? And so that's basically what we did. And here are some other of our early work, 2003 or so. Anna-Lene was one of my first PhD students, MD PhD student, actually. She is a professor and medical doctor in Münster, I believe, right now. But she we had 25 descriptors describing the structure of epophylones. And these are anti-cancer drugs. And we predicted the activity of certain derivatives of those drugs with neural networks and with support vector machines, which are a slightly different version of a machine learning technology at the time. Okay, and so I mentioned that the BCL has a bunch of those descriptors, and you will probably hear about those this week. I don't want to go into too much details, but some of the descriptors that we found useful are these radial distribution function or very similar autocorrelation functions. And I just wanted to tell you this to get one concept, and the concept is rotation and translation invariant descriptors. So when you describe the structure of these small molecules, if you shift them, the X, Y, and Z coordinates will change. And if you rotate them, the coordinates will change. And now there are neural networks that can work with that. There are neural networks where you can feed in a 3-dimensional representation, and they have the rotational and translational invariance built in at the time that obviously didn't exist. So we developed descriptors that are rotation and translation invariant. And so these would be distances and angles. And here's, for example, on the x-axis is distance, on the y-axis is intensity. And this is just a counting function. It counts how often you see a certain distance in this molecule. This is what this function does. If this difference gets 0, then this function becomes 1. And so you're just counting, and you have sort of a Gaussian kernel above that, so that you have, and then you bin this and read out the distance at every 0.1 angstrom, and that sort of gives you a profile. Now you can add some properties like partial charge or polarizability for the 2 atoms, and then the function changes, right? It only counts atoms that have a higher partial charge or a higher polarizability, and so on and so forth. And so you get different representation of your molecules, hydrogen bond donors, hydrogen bond acceptors, and you can just create a lot of numbers. And the chemists amongst you know the definition of a pharmacophore. A pharmacophore are the geometric and property features a small molecule needs to have to be active on a certain protein target. So there's a hypothesis that you need a small set of geometric and property features to make you active. And the challenge is to identify those. What functional groups and which geometric arrangement you need for activity. And the hypothesis here is we create thousands of these numbers with the hypothesis that the pharmacophore is amongst them. And then let the neural network identify the key properties and geometries needed for activity. Again, some of those things are moving these days with the new machine learning ideas, but at the time, this was definitely sort of the approach. Distances and angles don't encode stereochemistry, so image and mirror image are going to look the same. And so some of our research, we kept developing this library over the last 20 years when I had my group at Vanderbilt. And some of our research is, for example, how do we define stereochemistry in a way that a neural network can understand that, right? The chemists would say this is R, this is S, but that's bad for a neural network, right? And so a geometric way to encode stereochemistry is what we published in this paper, for example. Why did we not include the BCL into Rosetta when Rosetta was translated to C++? And there were a couple of reasons for that. The most important being that was right around the time when I started my own laboratory at Vanderbilt. And Aura will remember, and all of the young, I was amongst the first sort of set of PIs who became independent from David Baker's lab. And one of the things they all told us was that you need to have something other than Rosetta. If you just do Rosetta, you will not be necessarily recognized as an independent researcher from David Baker, and you should not build your whole career on Rosetta. You need something where you say, I'm doing something else. Even if I program Rosetta ligand, it will always be Rosetta and therefore David Baker. And so that was the reason why we continued to develop the BCL independently for a long, long time. To build sort of this area of research where we are orthogonal. However, in the lab, we always combined Rosetta with the BCL, and we programmed a lot of things into Rosetta in terms of small molecule handling and algorithms that were inspired by things that we did in the BCL. And in fact, since I got tenure, I explored with the Rosetta leadership, ways to integrate the BCL into Rosetta. It took longer than I hoped. Mostly, there were some legal questions, IP questions, but then mostly also just to get some hands to actually do it, because it requires work. And I'm exceptionally grateful that we have this workshop today, which means we did it. And the people who are organizing the workshop, Ben Brown and Jeff Mendenhall and Richard Parker and others, they put down the work to make this happen. So a big thanks to them, because I think combining these algorithms and having them at your fingertips within Rosetta certainly enables you to do things with small molecule drug discovery, combining some of these machine learning ideas with some of the Rosetta ligand code in very new and exciting ways. So I don't want to go into details of this paper, of the stereochemistry. You can sort of go ahead and read it. I also don't want to go into a ton of application papers. There are probably 50 papers where we use the BCL for drug discovery. So, and it's just going to be boring. I just want to make sure to mention that we have a track record using these algorithms successfully in real-world drug discovery examples. So this is we had a high throughput screen, 150,000 molecules, a very low hit rate, and none of those hits was a good starting point for drug discovery. So we trained a neural network and then used that neural network to screen a much larger external library where we could purchase molecules from, and then we purchased molecules that were predicted to be active and found at the time 12 novel chemotypes, 12 not just molecules, but 12 molecules of a new chemical structure that was not part of the primary screen. It's something that the chemists call scaffold hopping. And we were able to show that they are active on our target, which happens to be a G protein-coupled receptor in your brain, involved in anxiety and addiction. And these molecules that we found with the neural network were then chemically optimized in a chemistry laboratory. They, were derivatives synthesized and tested, and ultimately they were tested in animal experiments to confirm that they really have the activity that we were looking for. So again, I don't want to bore you with too many of these things. We have started to look at some of the concepts that are used in these neural networks. In particular, Jeff Mendenhall, who I believe going to present at some point in this week, tested top out with really good results in our neural network setup for drug discovery. So there is a paper that's not that long ago. We also spent a lot of work designing really good benchmark sets. I mean, I come out of the Rosetta community. We all know how important benchmarking is with respect to CASP and so on. And so in the drug discovery world, unfortunately, that was not as well established. And we put a lot of work into designing and publishing good benchmark sets for these kind of applications. So I think with that, I shared most of what I wanted to share. I'm happy to show you, additional examples of crazy code in here, how molecular coordinates are handled or how chemical shifts are computed. One of the things that BCL does really well, or some of my other, old programs that I programmed when I was an undergraduate or graduate student, including my own PyMold that does a three-dimensional visualization of proteins with different light sources and whatnot. But I think that would probably not be the most productive use of our time. And so I would rather, if people have questions about the BCL, it's probably more effective for me or the history of the BCL. I'm no longer, unfortunately, the expert for the current version, but if people have questions about this cheminformatics field and the history of the BCL code, I'm happy to answer those questions before you guys get a much better explanation of what the BCL can do today and what it can do in conjunction with Rosetta.
Thanks, Jens. Really appreciate the history. That was awesome. Yeah, so like Jens said, if anybody has any questions, we can open it up now. Just can be pretty casual. And then after we see if anybody has some questions, we can go ahead and move on to the next section. But we do have a few minutes if anybody has any.
Yeah, don't hesitate. People in my group know that I love to ramble about past times.
And we can put a timer on him too, so he can't spend more than a minute answering your particular question. Is getting Gas Tiger? Is he still around? Because he's somebody we could.
He is retired, and I again I talked with him a couple of years back when he was retiring and asked him to come by. He is still listed as Professor im Ruhestand. Let me show you at least a picture of the guy. He really, one of these guys you didn't realize as a student, but he really shaped what I was doing, right? So this is apparently when he was young, but this is more recent, I guess. So I think this is probably what I know. He has a Wikipedia entry, so there is probably a way to yeah, he's born 1941, and so it's German, so I'm not sure if there's an English version. Yeah.
We have his partial equalization for the orbital calculation for the partial charges in the BCL.
Yeah. We have in the BCL has some very fast algorithms to compute partial charges, which is also used in Rosetta. Actually, the Rosetta ligand uses partial charges, and one of the fastest and best ways to get these partial charges is the BCL. And this is partial equalization of orbital electrostatics, and it computes partial charges as well as polarizability along the sigma and the pi bonds in one go, and is really fast, much faster than any sort of quantum chemical calculation. And the accuracy is good enough for anything you want to do with Rosetta. But I think we also have another partial charge calculator in the BCL, because at some point there was a paper that said that different method gave better results. And so we had some student implement another partial charge calculator.
Yeah, we have a few. All right. Well, if nobody else has any questions, let's thank Jens again for donating his time to give this talk. This is really great. Now we have it recorded for posterity, so this is fantastic. Awesome. Thank you, Jens.
Yeah, and thanks to you guys again for putting this together. I hope that this will gain traction and people start to use the code in conjunction with Rosetta. I think there's a lot of potential these days.
All right. So I guess the next thing to do is to talk a little bit about what this workshop is going to accomplish, sort of why we're here. So like Jens said, something you may have noticed is that the BCL has been around for a long time. This is not new cheminformatics software. This is being actively developed and maintained by the Meiler Lab. We, in addition to things related to Jens' faculty development at Vanderbilt, we had challenges in the past in getting it integrated with Rosetta because we used some libraries that were commercial libraries for conformer generation, for example. And so sort of what happened at this point is due to more recent work from Jeff Mendenhall, we have gotten rid of some of those commercial libraries, and now we're able to do completely open source things, which paved the way to allow me to start to integrate it into Rosetta with assistance from Richard and Jeff, Rocco, Sergey, Steve, and all the people in the Rosetta community who could help with that. And so now, we're sort of at a point where we have the BCL. It's a more mature software package for cheminformatics, drug design. We've integrated it into Rosetta, which has a ton of great tools for structural modeling of proteins, and now we can do structure-based drug design. We have a bunch of really great newer grad students in the Meiler Lab in both Vanderbilt and in Leipzig doing cool new drug design algorithm work. And so this seemed like an appropriate time to start to say, well, hey, can we go through and teach everybody sort of the functionality that the BCL currently has and show them sort of where we're going with the Rosetta integration and how you can use the BCL Rosetta integration in your own projects. And I hope that this doesn't just serve as sort of a user manual for how to actually do some of these tasks, but also sort of sets the stage for where we are and what types of things we can continue to do, because there's a lot of potential for continued algorithm development in both categories. So the way that the workshop is set up, it is very tutorial centric. There will be short talks, not more than a half an hour, in between each of the tutorial sessions. The talks will generally just cover sort of conceptually what the purpose of the tutorials are for that particular section, as well as introduce people to some of the tasks that they may encounter in the tutorials. The reason why we wanted this to be a tutorial heavy and not just talks is largely because you don't learn as much just listening. It's also hard to maintain attention for more than a half an hour for any given talk. I say this from experience myself. And also because, you really do learn the most if you learn actively. And so we wanted to set it up so that way we're here to assist you as you go through the tutorials. We have sort of a designated time for it. We're also going to have all of these up on GitHub in the BCL Commons. And after the workshop's all over, we'll go ahead and probably make a lot of these things public. Not the code, obviously, but a lot of the tutorials themselves. And so with that, I'm going to go ahead and have a quick break since we're ahead of schedule, which is great. And then we're going to meet back here around 10 o'clock, and another graduate student in the lab, Wayne Boo, is going to start to go over the sort of command line syntax. So now that you have installed BCL, you're ready to use it, what are the commands, the sort of interface for how to make that happen. So in 15 minutes, we'll all meet back here, and we can begin the first talk.